Hey everyone, and welcome to The Explainer. Today we're cracking open one of the absolute most powerful tools in all of analytical chemistry. Think of it kind of like the ultimate secret code, or a highly specific chemical fingerprint that's used to identify the exact makeup of complex chemical mixtures. We are, of course, talking about the chromatogram. You know, if you've ever wondered how scientists know precisely what's in our water, our food, or even the atmosphere, well, it all really comes down to decoding this incredible visual data.
So, here's our roadmap for today. 1. What is a chromatogram? 2. Deciphering the two axes. 3. Retention and void times. 4. The ideal Gaussian peak. And finally, 5. Hyphenated analytical techniques.
Okay, let's dive right into Section 1. What is a chromatogram?
To really understand the complex science of trace analysis, we first have to nail down what a chromatogram actually is. Quite simply, a chromatogram is a two-dimensional diagram that reveals the instantaneous concentration of a solute exiting a column as a function of time. I mean, this graph is the absolute foundation of all chromatographic analysis. It's the literal trace, which, used to be captured on chart paper but is now reconstructed on a screen, that translates invisible chemical separations into a format we can actually see and measure. And this brilliantly illustrates the whole process. Looking at the physical separation happening inside the machine on the left, notice how that physical reality translates directly into the clear, digitized series of peaks on the right. Those three distinct peaks right there tell us that our original single solution was actually a mixture containing at least three separate components.
Moving right along to Section 2, Deciphering the Two Axes. Let's learn how to read this fingerprint.
To truly read it, we need to analyze the specific axes of this two-dimensional canvas. On our horizontal x-axis, the abscissa, we're tracking time, or alternatively, elution volume. On the vertical y-axis, the ordinate, we see the detector signal, which depends on the instantaneous concentration of our substance. Now, pay close attention to the baseline. That flat line is the trace obtained when there's absolutely no analyte present. Then, when a component separates, a peak rises up from that baseline. And here's a fantastic rule of thumb directly from our sources. You know your separation is completely finished when you see as many peaks returning to the baseline as there are components in your mixture.
All right, Section 3, retention and void times. Let's measure those peaks.
To really grasp how we measure the timing here, I want you to imagine a foot race. We basically have two very different types of finish times we need to record: the void time, denoted as Tm, and the retention time, denoted as Tr. Let's compare these two critical markers. First up is the void time, or V time. You'll actually sometimes hear this called the dead time. It's the time it takes for a compound that is completely unretained to just wash straight out of the column. Going back to our analogy, this is kind of like a runner who completely ignores all the hurdles on the track and just sprints straight from the start line to the finish line without being slowed down at all. On the flip side, we have the retention time, or Tr. This is the specific time taken between the moment of injection and the absolute peak maximum recorded on our chromatogram. This is the runner who actually interacts with the obstacles. And what's absolutely amazing here is that in an ideal case, this specific finish time is completely independent of the quantity of the mixture injected. Basically, a compound is going to have the same retention time whether you inject just a tiny bit or a whole lot.
Now, what's really interesting about this slide is how the timeline is laid out. That zero mark on the far left acts like the starting gun for both the void time, Tm, and the retention time, Tr. You can clearly see Tm happens super quickly, while Tr marks the exact summit of our peak a little later down the line.
Which brings us to Section 4, the ideal Gaussian peak. Let's look at some mathematical elegance.
Now that we have our timeline mapped out, let's transition into the mathematical beauty of the peak shapes themselves. Obviously, nature isn't always perfect, right? Real-world chromatograms can have peaks that are a bit asymmetrical or skewed. But the features of an ideal chromatogram are perfectly symmetrical. They precisely mirror a normal distribution of random errors, which mathematically we know as a Gaussian distribution. Look at how a true ideal chromatogram peak can be perfectly described by a probability density function. It isn't just some random blob on a screen, it's a highly predictable geometric shape with specific, calculable parameters.
In keeping with classical mathematical notation, these variables map directly to the visual anatomy of the peak we just looked at. Mu represents the retention time. That's the very center of our peak. Sigma is the standard deviation, representing the spread or width of the peak, while sigma squared represents the variance. Finally, y is simply the signal from our detector as time marches forward. It's so cool how the math perfectly aligns with the physical reality happening inside the column.
So, here is the absolute game changer. If the detector's signal varies linearly with the concentration of our analyte, then the area under the peak varies in exactly the same way. This is massive. It proves we can use the physical area of the shape on the graph to mathematically measure the exact quantity of a substance in our mixture.
And finally, Section 5, Hyphenated Analytical Techniques. Time to couple some instruments.
We've spent all this time establishing how incredibly precise the chromogram is, but here's a bit of a plot twist. According to our source material, the identification of a compound only by its retention time is somewhat arbitrary. A better method consists of using two different techniques that are complementary. Because, different compounds might occasionally share a similar retention time. If we want absolute, bulletproof scientific certainty, we need a major upgrade to our process.
This brings us to the immense power of hyphenated techniques. Here's how it works. Step 1, we separate the mixture completely using our chromatograph, creating those pristine peaks. Step 2, we physically couple the output online to a second instrument, like a mass spectrometer or an infrared spectrophotometer. Step 3, we obtain two completely different independent sets of data to confirm both the nature and the concentration of the components. We are essentially cross-referencing our chemical fingerprint with a chemical mugshot.
And get this, when we use these hyphenated techniques, we can measure concentration down to the nanogram. 1 nanogram is literally 1/1000th of a gram. It beautifully illustrates the extreme, microscopic precision these combined methods give us, allowing us to detect the absolute faintest trace of a chemical in a massive sample.
Which leaves us with a pretty fascinating question to ponder. If these incredible hyphenated techniques can translate a fluid mixture into a visual fingerprint and uncover the absolute chemical truth down to a single billionth of a gram, what other microscopic mysteries remain hidden in the noise of our world, just waiting for the right detector to graft them into existence? Thank you so much for joining me for this explainer. I really hope it brought the invisible chemical world into clear focus for you today.